My name is Jim Radigan. I am the dev manager for the C++ Cogen Technologies team. And they've asked me to come out and talk about some of the things that we've shipped, and primarily to talk about and touch on some of the aspects of the Clang hookup that we're doing for the Windows platform. So in a nutshell, I'm going to talk about some of the really great Cogen technology that we just shipped in June, and then I'm going to step back and try to demo some of the Clang compiler that we've built. Okay. And this will be what we're going to ship in November. So the first thing I want to do is acknowledge the Clang and Llvm community. I really have a sincere respect for everything that's been accomplished. It's been amazing. I've been looking over my shoulder since, 2007 and watching this thing grow, and it is truly, truly amazing. I think it started with Chris Latner and Evan Chang at Apple making some pretty huge contributions. And then recently, we've been talking to folks from Google with Chandler. And two folks are here today from Google to talk, probably after. So that is the full-on acknowledgement and a sincere thank you. So the mission for the talk is, I'm going to go into details about the new Cogeneration in 2015. Then I'm going to talk about how we use it to build the entire company. And then I'm going to talk about it also is used for building all the universal applications for C#. And I'm going to talk about how basically that work that we do every product cycle internally to build the company first before we retail the code generators accrues to Visual Studio. And now what's going to happen is I think that this work will accrue to the Clang and Llvm-based compilers for Windows, and it will also accrue back to Clang and Llvm itself as we try to help get that onto Windows. So everybody's seen this before, right? That's an Intel Pentium processor. And if you were to scale it today to the semiconductor processes that we have in flight, that's how big that scales. And the point I want to make with that is 2/3 of that is controlled by a compiler, basically the C2.dll at Microsoft, right? And so that's a very linear way of describing the world. But right now, Cogeneration is getting seriously far more complex than the standard CPUs that I was showing you right there. And if you think about it, you really have to begin to worry about FPGA. We're worrying about it now as far as being able to build acceleration in the cloud. That's going to be a major part of Microsoft's business. We also have to worry tremendously about something that's akin to inserting automatically MPI primitives so you can actually do distributed computing. And we really, really have to be realistic about attacking heterogeneous computing because the GPUs are just getting to be readily available and on chip with shared L3 cache. So that's a long-winded way of saying cogeneration really matters. And we have to get it right, and we have to be ahead in the industry on performance. And more importantly, we really, really worry a tremendous amount about security now, probably more than anybody else could ever imagine. So the compiler matters from a business point of view as well. So if you look at the amount of money that's been spent on Windows licenses and hardware alone in the last 5 years, that's what I got from Bloomberg. That's just what's been spent on Windows licenses alone, and then what's been spent on Intel hardware specifically. So that red arrow is the compiler. So we worry about throughput, absolute correctness. Anybody catch that? And then I just making sure everybody's paying attention. Code size, code quality. We build all of these across the company. We build them probably We build Windows quite a bit, but we build SQL and Office at least every 3 months to make sure everything's, and go through the enormous validation that's required to make sure that everything is correct. So how we work is important to know too, because as we do a lot of the things that we do, we're working within a context that is extremely difficult in terms of making sure we prove correctness at every step. So when we innovate, we don't add switches to the command line, can't afford the testing, so what we have to do is throw it at the wall, probably every day, right? And so what we're building is live compilers against the live Windows sources. And the Windows sources has at least 500 to 600 developers pounding every day with massive code flow that we see. So right there, anybody have a guess for what that is? Yep, that's 24 cores with a huge amount of memory, and it's only building one of the 5 full stack builds that we build every day. Live top a tree for the compiler and live top a stack for Windows. And that's before we do all the post-processing and then go on to run BVTs and app-compat, where we stage everything and distribute the images to about 750 machines, and we get that back within a 24-hour period. And if that comes back in that 24-hour period with one failure, we shut down checking into the compiler. Okay? That's the environment that we innovate in daily. So within that context, for Visual Studio 2015, we shipped new secure code generation, a new asynchronous programming model for C++, new auto-vectorization, a whole new framework for incremental whole program analysis. And we did a tremendous amount of work on build time. You can imagine that in our world, build time is a very, very big deal. So here's security. This is the simulation I did at the build talk, and I didn't get in trouble, so I'll do it again here. This is how a couple of guys in China hacked the Google Gmail client. So right here, you're going to create an image, and you're going to create an onload event, and you're going to pass that to F1. Here you're going to make a copy, and you're going to fail to do an add ref. So what's going to happen is that line right there is going to destroy the image tag object. What happens behind the scenes is the heap gets sprayed, the vtable gets hacked. We're going to call F2 asynchronously, and both image and event go out of scope, so they should be reclaimed. So you've got a use after free. And so what happens here is you're gone. That's it. So what we had to do was come up with a way to deal with this. And I named this slide Chum in the Water because we generate this code or something similar to it for every indirect function call. And the first time we put this out there, we recompiled and reissued huge parts of Windows 8.1 after it went out in order to deal with many of the hacks that were basically targeted at the Internet Explorer. And we didn't have to document much because the community did it for us. It was about a half hour before we actually got people watching blogs to see that everything we had put out was disassembled completely to the bone. So that's why I call it Chum in the Water. But basically, you can see what's going on here. The notion is that the pointer to the function that comes in ECX, we shift it, and then we use it to do a table lookup to see whether or not a bit is set indicating that the 8 bytes on x64 would be a valid target, a valid call target. So in order to do this, that's a graphic. There's the bitmap. And that what I'm showing there is the bitmap guarding those bytes in memory. And now what's happened is, to really ship this so that it could be used in a production environment, we spent far more time dealing with the overall system and interop. So what we had to do was modify the memory manager in Windows to make sure that the page tables didn't have backing store. We had to actually modify the OS loader. We had to modify the linker and the compiler, and those had to be paired as we distributed those with the OS loader. And the reason for that was that all of this has to interop so that you can link against code that has not been compiled with guard. And that turned out to be a 9-month saga, just that one interop story. So then we had to make small binary format changes, of course, for all the other tools. And we had to modify all of our binary static analysis. We have tools in the company that allow us to crack all the binaries, post-process them, write new code into them. And so reading these binaries actually got perturbed. So all the static binary processing, all of the operating system, and the tools all had to go out in one atomic lump sum across the company. So guard is a new compiler switch. It required close integration with the operating system. And it's completely interop. It should be seamless. You can do whatever you want across DLLs, and this whole thing works. And the response, you can imagine, has been, it was unnerving to be the first one to actually say we're going out there and be proactive to fight the bad guys. And so everybody held their breath for about 6 months. And one of the things we had to do is go down and recompile Adobe and Adobe Flash and all the digital rights management and all of that. And so far, it's been out there for a little over a year. We have moved the surface area of where these guys have to go. We've created an inconvenience, is what they've called it. But nobody's been able to crack the real mechanism itself. So, next topic on cogeneration. The clock rate's not increasing, right? So everything is going much more multi-core, much more parallel. So we have a new asynchronous programming model in Visual Studio 2015. We've introduced yield and await. We've created true coroutines for supporting these higher level language constructs. And they're far more efficient than anything that's out there or anything that we've done previously. So here's a really, really simple idea of what a coroutine is. Coroutine is just a way of, for the sake of the talk, making a stack frame, putting it in the heap, and then allowing that routine to suspend. And then since the heap contains that frame, you can always resume it for very cheap. So here's a great example. That's Fibonacci. Okay, there's main. And you'll notice the yield statement. So what happens now is every time we call fib, we're going to go to the routine on your left, and you see the yield statement, yield A. What's going to happen then is that will yield back A, and it'll set the coroutine up so that it can resume at the next instruction in that loop. Pretty straightforward. So what happens is during execution, we're going to actually save all the context registers in the code generation so that we make the code generation for creating the coroutine all be in the compiler, in the back end. We'll grow the frame. Then when we call, we'll actually create the coroutine on the heap, and then we're going to suspend. And then what we'll do is save the registers that are in the coroutine body. We'll unwind and restore the registers, and we're back. That's really pretty quick. That's what happened on each iteration of that loop. So that's yield, and this is await. I'm running a little behind, so I'm going to go quickly here. But that's a great way of writing a completely asynchronous TCP reader. And the impact of this is enormous across all the system programming internal to Microsoft now. This is being adopted by Windows in the kernel. It's going to be adopted by SQL. It's going to be adopted by Bing. And a lot of the network driver people, I think, are working with Gore Nishov today, who's the famous C++ author of coroutines. So one of the other pieces of code generation that we did is we spent an enormous amount of time vectorizing complex control flow. On the left is a loop that's very typical in a C++ language, so we have to actually deal with control flow. The basic concept is to actually mask the operations and then run both sides of the loop. And then what can happen is you'll OR things together with the mask. There's the other side, which is the else. So we execute both the left-hand side, both left-hand sides, each iteration of that loop. It's just that the results are masked to either use the original value or the new one that's computed based on what the condition in that if would have been for that particular iteration. So this really matters for Black-Scholes, for example, in the financial industry to do Monte Carlo simulation. What's going on here is on your left is the code that I've sort of summarized. And then on the right is the straight line vectorized code that you can get out of Visual Studio 2015. And this had a tremendous speed ups. So Black-Scholes is 600%. Numerical recipes, we've had some huge speed ups. It goes on and on and on. Being able to vectorize control flow is super important. So moving right along to build times, we actually took on the developer scenario and at great length. But there are two scenarios that I want to point out. One is the developer scenario, where you're incrementally building, which is really important if you're a game developer. The other one is the build lab scenario, where you're going to build Windows every night, top to bottom. Two completely different profiles. So here's our results for build time at a glance for 2013 versus 2015. You can see for Xbox, it's had a tremendous impact. There's Forza, there's Chrome, and there's the compiler itself. Those are some huge, huge changes. So one of the things that we did was incremental whole program analysis. Sorry, I reversed the order of these slides. But this is a chart that indicates the speedups that we've achieved in 2015, where 2015 is the orange bar. Now, incremental whole program is super hard. What that means is, if we're doing whole program analysis, we do a closed world assumption on pointers and aliases. And so we'll first build a call tree, and then we'll use the call tree to do a complete propagation of information up and down the call sites until that stabilizes. And then what we'll do is optimizations, and then what we'll do is final code generation. So even when you change one line of code or actually add white space, we were forced for correctness issues to completely recompile everything. What we've done in 2015 is develop the technology so that you can make modifications that are actually very meaningful and still get the right answer, and we will only at some times recompile one file. So here's an example of what I was talking about. So if you look at the slide, on the left, whole program analysis can prove that A, B, and C are not aliased. And then imagine about 100,000 other unchanged functions across 500 files. It's an enormous program, right? Which is not atypical of what we see. And so let's just say that you make a small change. So what happens is foo goes from what's on your left to what's on the right. And we've added a small read like that. Before, and with most compilers, you got to recompile the whole thing if you're compiling a whole program. So today we'll only compile one function. So what we've done is we've changed the workflow for the compiler. It used to be that for a full build, that's what you would do. You'd get CIL, which is our dump from the reader from which we would build the call tree. Then you would run the compiler, generate objects, link them, and of course you'd have your exe. So now what happens is we have an incremental PDB. And the incremental PDB, in a sense, stores a highly summarized form of data flow information and deltas that we can use to calculate for each iteration the minimum number of things that we have to recompile. So here are some of the scenarios that are huge wins for us from 2013 to 2015. One of the things we added in addition, I'm trying to go really quickly because we're running slow, is Debug Fast Link. And this was incredible for being able to do full system builds and cut the debug builds literally in half for many large programs. And basically what we did is we left the debug information in the OBJ files, and we created a dictionary PDB to cross-reference back to it. And then, of course, we had to change the tool sets to handle that ripple effect. So we also added profile-guided optimization for Xbox One. As you can see, one of the claims to fame early on was that Forza got a 14% improvement, and if you're somebody that makes money on just eking out frame rate, that was a really, really big deal. So this is where I'm going to transition the talk now. I'm going to start to talk about architecture. So Windows, we build Windows every day, and we target 4 different processors right now. So the code generators that are building Windows the code generators we ship are building Windows every day. They're also used to build SQL, Office, all of .NET, all of Visual Studio, and many Windows features internally. Okay? So code generation, to a lot of people, is responsible for instruction set architecture, in other words, generating the right instructions and just performance. But in reality, code generation is responsible for getting the ABI right, security, interop, runtime semantics, debugging, making sure GC is encoded correctly across different domains, and an ungodly amount of errors and warnings. So a lot of people look at code generation that way, right? Which is just simply, you're going to compile some C++, you're going to link it, and then what's going to happen is you're going to run that exe on the hardware. No big deal. Pretty straightforward. That's the world I see every day. I see compiling for frameworks and runtimes, as well as the executive layer of the operating system, in addition to all the other things that I just listed. And we do that for the managed side as well, because we take in MSIL. So the API and the ABI gets complicated because it's cross-barred with the hardware that we have to target. So if you think about it, all of this is unique to the hardware target. So that user.exe has to run against those runtimes, that nt.dll for that particular hardware, and all the code that we generate has to make sure that the interop between these runtimes and frameworks is correct. So there's an example of what I'm talking about. Back in this slide, the yellow arrows. Here's a great text example, or source code example. On your left is C++ calling into C++ CX. And then you've got C++ CX calling into C#. All of this is asynchronous. There are 3 different object semantics, and there are 3 different exception handling semantics across all of this. And so when something goes wrong, we have to tear down the frames and make sure there aren't any security problems. And we have to also make this extremely debuggable. So that gets complicated across all the architectures that we're targeting right now. And we have to have every one of those be mission critical correct. So top down, what I talked about here is a bottom-up view of cross-platform that we kind of see all the time and we're terrified by, frankly. There's another kind of cross-platform, which is top-down, and that's across platforms, actually across operating systems. So as you can see, the Clang front end is used on iOS and Android, and on Windows, we use what we call C1XX, and it's been around for a really, really long time. So what we had to do was create something like this for cross-platform. And the point is This takes care of the top-down view that I just showed you, and this takes care of the bottom-up view that I showed you with the 4 different architectures that we target. So all we did was create something pretty simple that is obvious that we take the Clang ASTs, we generate Llvm IR, we don't do anything else to it, and then we quickly go ahead and generate C2 tuples in our, which is the tuples are the name for our IL. So what we want to do is in November ship this. So for all 4 architectures, we'll have a top-down cross-platform story for code that would run on Android, iOS, or Windows. And then C2 takes care of all of the ABI and API and runtime semantics. So that's what we're shipping in November. So Clang for C2, this is about the status. We are at 99% correct for all of our internal testing across 4 architectures. That's with fully optimized code and with full debug support. We are also compiling in the stages right now of compiling many large applications and going for stress. So in V1 in November, there'll be many local changes. We were under pressure to get this thing done and out the door as soon as possible. So internally, we've got debug info, structured exception handling, a couple of lines for the bridge. We want to work with the community and contribute back as much as we can, because simultaneously, we are also committed to making sure that Clang and Llvm itself gets onto Windows. We really welcome the community. It's just that we have a different responsibility. So I think side by side, we're working together. And a lot of what we've finished here, we're going to be contributing back. We're still trying to figure out how to work with the community, and we're going really slow to make sure that we're actually being as deferential as possible and as respectful as possible to what it's like to work in the community, because it's a new experience for us all. And we want to make sure we do that right. So in February, we're going to hopefully, at that time, have contributed everything back. There'll be no local changes except for our 3-line hack to get us into UTC. And at that point, we should be having a whole set of new discussions about a lot of the new architectures that I showed you in that diagram, where we're talking about FPGAs and heterogeneous computing. So for those of you in the audience that are Clang OSS, Clang open source people, this is the 3 lines of change, okay? I see people shaking their head, which means that's good. I spelled the function calls right, and I got the drift of files right. So basically what we're doing is we're loading the c2.dll, creating a Clang object. We're initializing C2, and then finally, in Cogen action, which is pretty obvious, we call Clang invoke compiler pass W for Windows. That name isn't very imaginative. So this is where we are today, and this is one way that we could go. We could actually open it up so that Llvm becomes far larger and contributes much more to the platform in terms of optimizations, and also being able to consume bitcode, which I'll get to. The other way this can go is, which is super cool, and if you're a nerd, I'm dying to run this experiment, which is to run both optimizers at the same time. That's the supercharged. And I think that, barring anybody caring about compile time, would be a really, really interesting experiment. So again, we're going to be doing this while we're helping the Clang and Llvm community proper get onto Windows. The other thing that's really important to call out, and we want to take full advantage of this, and this is some of the other features that I'm going to get to, is that we'll be able to read and write Llvm bitcode. So in a sense, you can say that we will at least set up a system where Llvm bitcode could be seen as a universal input to Cogeneration for all the Windows APIs and ABIs that we have to deal with. I think that's an exciting longer-term thing to discuss. So for the community, we promise we will never fork. We will help Clang and Llvm. Clang C2 is read-only and 3 lines of change. We're never going to try to push this back to the community. We don't think that anybody in the community would ever take this and test that path. And one of the things that I think after talking to Chandler Carruth, I wanted to make sure was crystal clear is that we're not going to try to propose changes to Clang and Llvm that would be bothersome and unique to the C2.dll implementation. We want to completely treat the internal data structures in Clang and Llvm as read-only, and we will deal with any difficulties through versioning. So we should be off the radar screen. But for the other project, we have people helping to contribute. I think people are helping with the debug information right now. I think people are helping with structured exception handling. And I think, Gore, you're helping with await, or people are talking to you about await?
We're talking about await.
All right. Those are just some examples of the collaboration that have just begun. It's a brave new era, right? We're all one big happy family, Apple, Google, and Microsoft, all right? What the hell? So, so C++, universal language, universal cross-platform, except for this part of the language, if-def, right? That throws a monkey wrench into it. Whoops. So it turns out that if you're writing a bunch of cross-platform code, you wind up putting if-defs in there just to deal with implementation details. So this is a really big deal for us. The strategy for the company is that if all of this code runs on Android or it runs on iOS, it should run over here without having to do any of those if-defs. But that Swiss cheese on the left is the reality, okay? So our goal with the Clang C2 hookup is all of these yellow ellipses are going to go away. So here's an example of 4 categories that I could find for if-defs when we looked across Minecraft and we looked across Bing Maps, which I'll show you in a little bit, that contains a huge amount of cross-platform library code. So there are if-defs for missing C++ standards conformance. There are an enormous number of if-defs for errors and warnings. Everybody should raise their hand, right? Everybody wants warnings to be as errors when you build, right? Nobody if-defs anything off. And then there are if-defs in there for bugs, and there are if-defs for dealing with libraries and library APIs based on compilers. So here's an example of what will now compile. This will get rid of a whole bunch of those yellow ellipses. All of this code, if this were to appear in that Android code, the C++ Microsoft compiler couldn't compile variadic templates, variable templates. Sorry. That's our front end guy. So then non-static data member initializations for aggregates and nested namespaces. Those are 3 prime examples of missing conformance. Then things like this will go away. This is the inverse of what you'd expect, so I showed this first. We actually see this. This will go away. This kind of a warning. And of course, naturally, these types of warnings will go away. And then here's an example of a template bug that would go away. And imagine how long it takes to figure these things out. Just that we treated this, we chop it and don't treat it as a true 64-bit. And it winds up having to be cast to make sure that we get the right type so that it comes out to be 4 billion. But that's just one example of a compiler implementation bug that causes that Swiss cheese that I showed you on the left. So measurements. As of Friday, this project has been deeply studied. Here we are with the compile time what I wanted to do was actually look at compile time as a broad spectrum, which you have to. And every time I go and do performance analysis, it never ceases to amaze me, if you're going to be a good engineer, how incredibly rigid you have to be about snapping a really good baseline and being absolutely objective. So bear with me, this is not as full as you would like because I just didn't feel since Friday that I had been doing the due diligence required, but everything I do present here is something that I do believe is absolutely correct. So if you're compiling C, what we did is we compiled GCC, and as you can see, we broke down the overall compile time for spec2k6 GCC, and then this is the front end component, and then this is the bridge and the back end component. And you can see that if this is one core, no multi-threading, no parallelism in the build system, and it's O2 without Pogo, that those numbers show that for C, it's starting to look like the Microsoft C front end is faster. If you just go and compile spec2k6 Xalang, right, that's a real good representative for C++. I would never write an XML parser that way, but it's a great example of C++. And right now, it looks like this is where the two front ends are break even. And then we have this other benchmark, which is computing eigenvalues, and it is super heavily templated C++. And here we can see that what happens is Clang C2 winds up being significantly faster. So if you were to actually look at it, and it kind of instinctively makes sense if you look at basically the age of the compilers, right? As you go from the left, it seems like the Microsoft front end is faster, and then as you go to the right, it seems like Clang becomes faster. And it makes sense because of the parsing technologies upon which each of the front ends is built. So I feel pretty good that that makes sense. So what's really cool is if you look at the bridge itself, where we convert Llvm to our IR tuples in C2, it looks like, here's a vtune profile. It's not until you get down here in a profile that you can actually begin to see the bridge itself after we read. And so the punchline is that that yellow column represents all of the cycles that we use to compile the eigenvalue benchmark. And it's 56 trillion, so it's 56 times 10 to the 9, and that's 226 times 10 to the 6. So basically, it's really about 0.043% so far, just for the reader cleanup. So all up, it's less than 1%. Whoops. So here's performance of the Cogeneration that we're producing today. We've got what we feel is we're on par for things that really, really matter. It turns out that the vectorizer has to jump through hoops in order to vectorize the key integer loop in this, and when you do, you actually speed it up by 2. Good luck on vectorizing that. This loop alone, when we generate code for the inner loop in this, we generate about 53 runtime disambiguation checks before you enter into the key loop, and it still speeds it up by 2. And the code size is, quadruple. Then this is another integer vectorizer, and Soplex, that's another integer vectorizer. So we've got a really good handle on this, and we think that when we ship in November, we'll be on par with O2 for the existing Microsoft compiler. And if you think about it, we started in January. That's pretty good. And one of the things we have, this is a real litmus test. There's a real, this has been seriously painful for us, and I'm sure it hurts at other compiler teams. If you want to vectorize this loop, you got to rewrite it to just do the analysis. And if you do the analysis and you find out you can't vectorize it, then you have to not impact the performance after that rewrite, which was basically fake to just do the analysis. Somehow we've got to get a primary induction variable out of this loop and make all the memory references have symbolic linear expressions before we can actually automatically vectorize and then automatically parallelize this loop. And that's really key to performance today. Without that, you can't really compete in the cogen space on all the chips. So nothing would be complete without a demo. So how am I doing for time? Okay. So one of the things that I'm going to start with, this is not why we did Clang. C99 is probably, when I looked, I couldn't believe it. It was, somebody put it out there on user voice that we didn't compile C99. We hear you, we care about C, and then when I look back today, there are over 1,000 user upvotes on that one. So that one actually is a really big deal. So I'm going to demo that so that people believe in me. Because I said we were going to do that 6 months ago. And let's see. So what I'm going to do is I'm going to, let's see, let me bring this up. So there you go. There is some good old-fashioned C99.
Very soothing.
I'm soothed, but it's not.
Every time you hit these keys, how's that? There we go. All right, so there you see complex double, complex double. This is a call into the C library doing a complex absolute value. And as you look below, you can see all the C-style initialization for complex and imaginary, or the real and imaginaries. And so no demo would be complete doing C99 without there I am calling, as you can see, standard C99, and then I type Mandelbrot.exe, and then there we go. Yay, complex for real. Okay. So coming back, one of the other demos I'm going to do is structured exception handling. One of the things we found, it was really, really easy to quickly bring up exception handling using the 3.6 compiler. And what we're going to do is once the guys at Google get it to the new design to completion, we'll consume that and we'll throw away whatever we've done internally, locally. But one of the things that's really difficult, and you can imagine, I think we just, in order to help the community, put all of our structured exception handling tests out there. And so one of the tests I was going to show you is except for you. That's a good example of some structured exception handling on the left. And you can see it's nested, and it's got a complex filter. And there are over 95 permutations of this, and with much deeper nesting, with go-tos, with rethrows, you name it. This is one of those files that I'm sure we didn't release this little tidbit, right? But this started back in 1990. And this thing has grown, and when something would break in this file, that guy would actually send you email personally on the compiler team. We all lived in terror when this was coming up. So what I'm going to show you then is that we can compile except for you. We have except for everybody, right? So let's see. I'm going to go quickly. There we go. I compiled that before, but I want to actually, we're about to run out of time. Basically, the whole thing passes. It passes O2. And now the other thing that I wanted to show you really quickly, which is much bigger, was this is Big Maps. And it is an enormous program. And it consists right now of 10 cross-platform libraries, all of which compile and run on Android. And what I'm going to show you then on another laptop is that, in fact, this will, if you can bear with me, hopefully this is still working. You guys see that or not? I'm Yuri. Thank you very little.
Nobody saw it.
And I do owe Yuri a bottle of wine. Okay, so what I wanted to show here was we're breaking in read token. And if you look at this, F10, here are all the cross-platform libraries off to your left where the cursor is moving. And what I've done is I've just stopped here on what is a JSON token. And if I go to the right and then pull this down, I can still use the JSON visualizer right there. That did work yesterday. Is that right? Oh. Shift F5. F5. Okay, there's the reader being constructed in Clang or in JSON with the Clang compiler, and then F5. Here we are. So I just hit F10, and now there's the token F10. Did I go the wrong way? There we go. So the point I just wanted to make, though, was that within the context of an enormous source base with 10 cross-platform libraries compiled with Clang C2, we're running big maps, and this is to indicate scale and credibility of the project before we're about to ship it in November. So with that, I want to say thanks. That's an overview of the project, and any questions? Hi.
You were talking about implementation aside from being keywords on an implementation level. How are those different from libraries that are already?
Oh, there is no OS support whatsoever for this. What happens is that the support for the abstraction is completely carried out by the back end of the compiler working in conjunction with libraries. And the only overhead is actually creating a frame in the heap for a coroutine. So there's 0 fiber, 0 OS, and
Directly being generated by
exactly. And that's why we consider it to be very innovative and very impactful, because the overhead for large asynchronous source bases gets cut in half many times. And one of the things that's really important is that that size savings for asynchronous programming is huge on phones. So asynchronous programming on a phone with, very, very tight constraints, actually, this is an enabling technology to get a lot of applications to fit. So .then in C++ CX, every instance of that we found was originally taking, how many bytes was that, Steve? About 5K when we first looked at it? Yeah. For each instance of .then. And now what it could be is on the order of 40 bytes. Oh, the guy's showing me the sign, repeat question. The question was about coroutines, yield and await, and whether or not we were working with fibers or any other OS abstractions. And so the answer is 0. Oh, Gore is right here. Gore is the real genius behind the implementation. I just worked for Gore as a Cogeneration guy.
I'm the parser.
But we wound up building something that I think is really pretty significant for asynchronous programming in C++. So, sorry. That's what we're trying to shoot for. I don't know about that. There is going to be a need to filter Windows header files, right? Which is your knob for how much of that stuff you want. That knob has to stay, I think.
It sounds like a lot of your products have moved towards the C1 thing, like you mentioned SQL Server and all these other things.
What's the C1 thing?
C2. Like using the C2 front end, like to actually build these products. Yes.
Oh, no. So that in a couple of years, like say 5 years out, it would be great to converge on one front end. The size of the legacy source bases and the amount of uniqueness in the C++ that we compile, just for SQL, Office, in fact, DevDiv itself. One of the interesting, my team is about to ship, there are 3 places that I hold my breath on across the company when we compile. One is the .NET framework, because they thunk everything all over the place and use ASM. And you can imagine what that's like on 4 architectures. The other part is structured exception handling in Windows. And then the other part is C++ exception handling in SQL, the way those teams use that. And all of that, and all of the asynchronous complexities to get correctness is quite a ways off, given how unique the source bases are to Windows and having been around for 5 to 10 years. Oh, I'm sorry. We have 2.
No, I think you answered my question. I just phrased it wrong. Like I was really getting at, like, is it a goal, like, or a desire to converge on one?
It would be a goal, and it definitely is a very strong desire to converge on Clang. It really would be a win. But I can assure you that it's a long ways off. And in the meantime, we have a responsibility to the stockholder, right, which is to continue to build the company, continue to innovate in security and performance, and bring a lot of those source bases to new processors that we're coming out with. So that's why we're very interested in getting Clang and Llvm onto Windows while we're doing this simultaneously. Everybody wins if there's fewer front ends.
So when you mentioned like SQL Server and all these things, are you able to compile them with Clang right now, like even internally?
We can compile parts of each of them, but it's, you know, it's not significant enough right now. No way. In fact, maybe 10% of Windows.
Years ago, you guys rewrote the whole rewrote the process. The question is, Clang is in front end. It goes quite nicely already.
Steve? You're going to have to yell.
Hi, I'm Steve.
Steve is the front-end dev manager and the IDE.
So we already, when we shipped Android support in RTM, we already had a mode inside of Elephant to set it to be like in Clang mode. We use EGN covers for that, but it can already kind of emulate in the CMX stack, which is the default Microsoft front end, and also I think it's Clang front end. It works pretty well.
One of the things that's really hard in the IDE environment when you're typing in, right, that front end that parses the language is actually shifted into a whole nother mode where it's parsing with incomplete and incorrect by default, right? So that's another large ball. So we're going there, we want to, and converging actually saves a tremendous amount of money. And I think it would be really cool to actually have the community be able to contribute directly to the things that we compile, compile with.
Follow-up, it's not a technical question, but is this a new kind of Microsoft? Is there a time, a year or 2 years ago, where you saw like a sea change or potential flipped over to the other side, this kind of collaboration and not trying?
Was there some major event?
To be honest with you, internally, we're just like you guys, right? It's common sense. We like to work with other smart people. And I think we've always been this way. But also, one of the things you should know is, and this is a real hidden aspect, but we have unbelievably tight schedules, and we run with really, really small teams. So even though we have the best of intentions, right, they have to allow us the time to actually do the collaboration. And so that would be what I would consider to be the only change, really. You should have been here in June when we shut down. I've heard about that. Yeah, and now that we're here, right, we actually have the ability to experiment in some really, really interesting ways, I think, like you're pointing out. So if we go back to that slide, which I think is really an important thing for the audience. You guys see that? Yeah. Right, we can go that way, or we can go that way. Again, it's a matter of correctness. We have to guarantee mission-critical correctness across an enormous amount of code. What this compiler compiles, if you look at what the numbers are from telemetry, it's enormous. And it's gotten to the point where people actually think if there's a compiler bug, it's like a hardware bug, and you guys have lost your mind. What are you doing, right? And so the overhead for the more you add, the more stuff you break becomes something we really look at. So we could allow that switch to be out there, but we haven't figured out a model where we could ship things where it's sort of as is. Question? Yeah. I didn't want to embellish that one at all. Absolutely. In fact, that's one of the big value adds, Having, not been exactly the sharpest template programmer in the world, I could actually see the difference right away and was able to be much more productive with the warnings and errors that I got from the Clang front end. So that's a personal endorsement right there, right? That's a whole day of pain in templates, right?
What about things like the compiler intrinsics and the STL?
Yeah, we're shipping STL with this, and we are, yeah.
Would it be able to compile against the standard C++ like C++ correctly? Or would there be like compiler-specific features there that would not compile?
Yeah, go ahead.
So we're starting with cross-platform. We want to get cross-platform. The intention here is there are a lot of things we can't do with this, but for the short term, what we want to do is using Visual Studio as a cross-platform development. Then you get the ability to use the same framework on those libraries that are shared. Right? So in the short term, the idea is that we'll use our own library. Once we get past this milestone, actually ship how we do things like add and type hardware
We want to be able to actually use every bit of the technology in the Clang front end that we can. The difficulty is going to be, realizing that the implicit contracts and explicit contracts that we usually have for shipping compilers is going to have to change. So there is a thing that we're going to have to go through internally and culturally, which is we're going to ship in November. That'll allow everybody to kick the tires, and then finally that'll be as is. That's going to be out of band, but within Visual Studio. And then by February, we culturally should have an idea of how to handle the contract with the customer. Chandler? Okay. We have found, though, that, oh boy, you're right. Okay. So any other questions? Any other follow-up? Just feel free to email me at Microsoft. It's jradigan@microsoft.com. Okay? Thanks.